Barrier Diodes, SBDs in short, are diodes, two-terminal devices, but these diodes are formed out of metal semiconductor junctions. Metals used are molybdenum, platinum, chromium, tungsten, etc. And semiconductors that are used widely are N-type silicon materials. P-type materials semiconductors can also be used, but their use is very rare. Important feature of these diodes is that they are capable of rectifying even very high frequency signals. They can work even at such a high frequencies like microwaves. They find in the design of mixers used in radar systems. They also find applications in clamping circuits, in AC to DC converters of high frequency signals. In such several other areas also, they find their usage. And what is the reason for their use, for their usability at high frequencies? One reason is it's a forward voltage drop is very small when compared to ordinary PN junction devices. Another reason is their capacitance, SBDs capacitance, both under forward direction as well as reverse direction. These capacitances are very small, so small when compared to ordinary PN junction diodes. Presence of capacitance in any device means making the device lethargic, making the device slow. So low capacitance means system or device, it becomes fast, very fast. Net result is switching times, changing times from one state to another state. It becomes very less. when we use SBDs when compared to PN junction diodes. So fast switching times is an important aspect. For this reason, its usage it has gone to a very high frequency levels, high frequency applications like radars. Special diodes, Schottky Barrier Diodes, series on semiconductor devices and circuits, lecture number 2.26. Schottky Barrier Diodes, they belong to the category of special diodes. They are made out of a piece of metal and a piece of semiconductor. In that way, they are different from ordinary PN junction diodes, which are made with two pieces of semiconductor. Schottky barrier diodes, or SBDs in short, they exhibit rectifying properties. They are well known for their high switching speeds and low noise figures. For this reason, they are widely used at higher frequencies like microwaves. With this small introduction, now let us move further into the core session where many more interesting and significant points regarding SBDs are introduced and described. We begin the discussion with a few introductory remarks on SBDs. Schottky Barrier Diode, or SBD, is named after German physicist Walter H. Schottky. These diodes are also known as surface barrier diodes or hot carrier diodes. The voltage current characteristic of these diodes is similar to ordinary PN junction diodes. It means SBDs, they have the rectifying properties similar to ordinary PN junction diodes. In one direction, they exhibit higher amount of resistance. In the other direction, they exhibit lower amount of resistance. But with a significant difference with the PN junction diodes. So that is the cut-in voltage in SBDs is much lower than ordinary PN junction diodes. What is the cut-in voltage? Consider forward biased characteristic of an ordinary PN junction diode. It is exponential. Essentially, it appears like this. But notice the rise in current is not there until the forward biased voltage is more than certain voltage. This voltage is called cut-in voltage. This cut-in voltage is much smaller. It is very, very small in SBDs when compared to ordinary PN junction diodes. So one can write forward biased characteristic of SBD like this. V gamma is cut-in voltage is very, very small. It is a metal semiconductor diode, as already mentioned, and with a low forward voltage drop. In normal silicon diode, voltage drop under forward bias lies in between 0.6 to 0.7 volts, whereas in a Schottky diode, this drop is between 0.15 to 0.45. So a significant feature of SBDs is its low forward voltage drop. It lies in between 0.15 to 0.45 volts. This lower voltage drop facilitates a higher switching speed and better system efficiency. Higher switching speed implies higher bandwidths and also suitability for high frequency operation at frequencies like microwaves. Metals used in their construction for their fabrication includes molybdenum, platinum, chromium, and tungsten. Apart from these metals, certain silicides like palladium silicide and platinum silicide are also used. The choice of metal semiconductor combination, it determines the exact value of voltage drop. The work function of semiconductor should be larger than that of metal. While choosing metal semiconductor combination, certain precautions must be taken. What is that? What are those? One such precaution is work function of semiconductor should be larger than that of metal. Usually, semiconductor is of N-type silicon. The P-type is not preferred because their large reverse leakage current. These diodes are also endowed with the zero diffusion capacitance CD and a smaller transition capacitance CT than ordinary PN junction diode. Diodes, PN junction diodes, they are associated with the two types of capacitances, diffusion capacitance, transition capacitance. First one under forward biased condition and second one under reverse biased condition. First one's diffusion capacitance usually large when compared to the second one, that is transition capacitance. In case of SBDs, CD is almost zero and CT, that is transition capacitance, it is smaller than PN junction diode. Notice capacitance, existence of capacitance inside diode, it limits the frequency of operation or maximum frequency of operation. It limits bandwidth. It introduces sluggishness into the operation of diode. Lower capacitance means higher frequency of operation, greater bandwidth. Some more points regarding these diodes. SBDs employ Schottky barrier, which is a potential energy barrier for electrons formed at a metal semiconductor junction. These barriers exhibit rectifying characteristics and are associated with a barrier lowering phenomena called Schottky effect. From Schottky barrier, the name Schottky Barrier Diode has come into being. Barrier formation. When metal and N-type semiconductor come into contact for the first time, electrons diffuse from the semiconductor to metal, establishing a field from semiconductor towards metal and a potential barrier preventing the flow of electrons further towards metal. Here, the formation of barrier is being described. The field then encourages electrons to drift from metal to semiconductor, thereby lowering the barrier and weakening the field. This leads to diffusion, raising the barrier, then drift, lowering it until an equilibrium is established where a barrier exists with a stable height. So initially there exists diffusion when metal and n-type semiconductor are brought in contact to each other. Electron diffusion takes place, then electrons drift takes place in the opposite direction, then diffusion, then drift. It continues for some time until there exists an equilibrium, a barrier with a stable height. When the negative charges are brought near a metal surface, positive charges are induced in the metal. This is a phenomena that can be understood very easily. Induction. When this image force is combined with an applied electric field, the effective work function is somewhat reduced, leading to barrier reduction. Note, not all metal semiconductor junctions form a rectifying Schottky barrier. Some junctions conduct current in both directions without rectification, and these are called ohmic contacts. There are two types of contacts: ohmic contacts, rectifying contacts. Ohmic contacts, they just offer certain resistance, non-rectifying resistance to the current flow, whereas rectifying contacts, they rectify the current too. Rectifying a contact formation. Phi m more than phi s. In case of n-type semiconductor, phi m less than phi s in case of p-type semiconductor. Here phi m is work function of metal and phi s is that of semiconductor. So phi m means work function of metal. It should be more than work function of semiconductor when it is n-type for the formation of rectifying contact. When the semiconductor involved in the contact formation is p-type, then phi m should be less than phi s for the formation of rectifying a contact. Diode junctions tend to form between the silicide and lightly doped n-type region. Ohmic contact formation. When phi m is more than phi s p-type and phi m is less than phi s n-type, ohmic contact formation takes place. Ohmic contacts are found to form between silicide and heavily doped N or p-type region. Here, some information is being given regarding the formation of rectifying contacts and ohmic contacts. The symbol of the diode SBD is shown here: anode, cathode, ordinary diode symbol with some modification. In B is shown constructional details: metal, aluminum, n-type silicon, anode, cathode, and energy band diagram of Schottky barrier under zero bias. In the diagram, phi b is the barrier height, energy, Fermi energy, EF, EC, conduction band level, valency band energy level. Notice Fermi is in between EV and EC. Some more points. One of the primary characteristics of a Schottky barrier is its height, denoted by phi b, whose value depends upon metal semiconductor combination. Barrier height is the difference between the interfacial conduction band edge EZ and Fermi level EF. In case of p-type semiconductors, it is the difference between EF and valency band edge EV. The barrier between a metal semiconductor junction is predicted by the Schottky Mod Rule, which says barrier height is proportional to the difference of the metal vacuum work function and semiconductor vacuum electron affinity. So the underlying principle for the formation of SBDs, it is given by Schottky Mod Rule. In Schottky diode, the barrier is high and a depletion region exists in the semiconductor near the interface. The barrier exhibits a high resistance when small voltages are applied. Under large voltage bias, the electrical current through the barrier is essentially governed by the laws of thermionic emission and the fact that Schottky barrier is fixed relative to metal's Fermi level. Energy band diagram of SBDs. They are given here. A shows the energy levels under reverse bias, B shows energy levels under forward bias, C shows under forward bias, but it exhibits energy levels when the barrier height is very high. White arrow shows the injection of an electron hole into semiconductor's valence band. As already mentioned, EF stands for Fermi level, EC, conduction band level, valency band level, respectively. Here, arrows you can see. Arrow shows the injection of electron hole into semiconductor's valency band. It is not a white arrow, it is black arrow. Now, rectification properties of SBDs. They are explained, described here. Forward biased SBDs with N-type semiconductor. The Fermi energy of the metal, it is lowered with respect to the Fermi energy in the semiconductor. This results in a smaller potential drop across the semiconductor. The balance between diffusion and drift is disturbed and more thermally excited electrons will diffuse towards the metal than the number drifting into semiconductor. This leads to a positive current through the junction at a voltage comparable to the built-in potential. Hence, a large current exists under forward bias. This current rises very rapidly with the bias, but at high biases, the series resistance of the semiconductor start limiting the current. For a very high SBD with a large barrier height, the forward bias current is carried by minority carrier injection. So this explains how and why large current flows when Schottky barrier is forward biased. Now we consider reverse biased Schottky barrier diodes with N-type semiconductor. The Fermi energy of the metal is raised with respect to the Fermi energy of the semiconductor. The potential across the semiconductor now increases, yielding a larger depletion region and a larger electric field at the interface. The barrier which restricts the electrons to the metal is unchanged so that the flow of electrons is limited by that barrier independent of the applied voltage. The metal semiconductor junction with a positive barrier height has therefore a pronounced rectifying behavior, while almost no current exists under reverse bias. Actually, there exists a small leakage current of thermally excited electrons in the metal crossing the barrier. Usually it is constant, and at very high bias voltages, the breakdown of depletion region takes place. A few points regarding applications of SBDs. Due to its quick response time and low noise figure, Schottky diodes are used in high-frequency radar systems, mixers, detectors of communication systems, and also in instrumentation. Nowadays, they are also being used in voltage clamping, reverse current and discharge protection, low voltage, high current power supplies, and AC to DC converters. Due to their lower forward voltage drop, they are also used in voltage clamping applications and prevention of transistor saturation. They have become most efficient choice for applications like stand-alone photovoltaic systems to prevent batteries from discharging through the solar panels at night. And in those applications, they are called blocking diodes. With this, we come to the end of the session. Before going to close down, let us recollect the important areas, important points that are discussed in the session. An introduction to metal semiconductor diodes, it has been given. The energy band diagrams pertaining to Schottky barrier contact, rectifying contact, and a non-rectifying contact between metal semiconductors. Information pertaining to them, it is provided, and then symbol VI characteristics, they are explained. At the end, a brief on applications of SBDs, it is given. Hope this session is useful to you. We meet again in another session with a new topic soon.